In order to understand human biology, we need to know about cells. But in order to understand about cells, we're going to need to know some basic chemistry. So that's what we're going to do here today. Just the basics, what you need to know to get by in this course. We'll need to start out with some basic terminology. The first term is matter. Matter is anything that has weight and takes up space. So your desk could be considered matter, or the plant that sits in your windowsill, or even you're made up of matter. The next definition are elements. Elements are the basic building blocks of matter, and elements cannot be broken down by chemical means. On Earth, there are 92 elements that occur naturally, but what you'll see is that there are 4 major elements that comprise the human body. Those elements are carbon, nitrogen, oxygen, and hydrogen. Another important definition for us are atoms. Atoms are the smallest units of an element that still retain that element's physical and chemical properties. Atoms bond together to form molecules. What you see here is an excerpt from the periodic table. What you should notice is that the elements here are arranged in a certain way. Each column within the periodic table includes elements that behave similarly to each other in a chemical reaction. So if we look at, say, hydrogen here along with lithium, sodium, and potassium, each of these elements would behave similarly in the same type of chemical reaction. Atoms can be further divided into their subatomic particles. Each atom has a central nucleus, and then around that nucleus are pathways called orbits. What comprises the nucleus are subatomic particles called neutrons and protons. Neutrons have a neutral charge. That's easy to remember. Neutrons are neutral. Protons, P for positive. Protons have a positive charge. And then electrons are negatively charged, and electrons orbit around the nucleus. So what you see down here is a nice little handy-dandy chart to help you remember each of these particles' charges, and later what we'll look at, its atomic mass. So protons have a positive charge of 1, neutrons are neutral, they have a charge of 0, and electrons are negative, they have a charge of -1. Each orbital that surrounds the central nucleus can hold up to 2 electrons, and when electrons enter, the inner orbitals get filled first. Those inner orbitals have the lowest energy levels, and as we go to the outer orbitals, there's more energy in those orbitals. So what you can see here is the element hydrogen. It has 1 electron. That 1 electron fills the innermost orbital. If we go and look at carbon, another element, what you'll see is that it has 6 electrons. The first 2 electrons fill up the inner orbital, and now what you see here in the rest of these cartoons is that the orbitals have been now grouped into shells. And so shells, the innermost shell has 2 electrons in them, and all of the other shells have 8 electrons, up to 8 electrons in them. So what you see here in carbon is the innermost shell, which contains 1 orbital, has 2 electrons in it. And then the second shell, which could have up to 8 electrons in it, has 1, 2, 3, 4 electrons in it. That gives carbon a total of 6 electrons. In order to be electrically neutral, an atom must have the same number of protons and electrons so that we have a balance of the positive and the negative charges. If you look on the periodic table, the atomic number tells us how many protons, and therefore how many electrons, an atom has when it's electrically neutral. So the number of protons will have to equal the number of electrons. We can measure the mass of subatomic particles in atomic mass units, or AMUs. The mass of a proton is 1 AMU. The mass of an electron is 0.00055 AMUs. The mass of a neutron is 1 AMU. So for all practical purposes, the mass of an electron is pretty much nothing. So we can disregard that when we do anything that involves calculating the mass of something. So the mass of a proton is 1, the mass of a neutron is 1. The sum of the protons and the neutrons in the nucleus of an atom is the mass number. So when you see something like carbon-12, that means that there are 12 protons plus neutrons in the nucleus. So let's take another look here at the periodic table, and let's see what else we can see. The first thing I want to point out here is the atomic symbol. So this is the letter that describes each one of these elements. That's what tells us which element we're talking about. The second thing that you'll note is the atomic number. So that's the number up above each element's atomic symbol. So this is hydrogen, its atomic number is 1. And then the third thing we can get from the periodic table is the atomic mass. That's the number you see on the bottom of each of these squares for each of these elements. We can do some basic math from what we see here. We said that the atomic mass, anything that involves mass, is going to disregard electrons. So the atomic mass here for hydrogen is about 1. That's the number of protons and neutrons. The atomic number is also going to be the number of protons. So hydrogen has 1 proton. It has 1 protons plus neutrons. So hydrogen would have 0 neutrons. We can do the same thing here for carbon. The atomic number is 6, so that means there are 6 protons in carbon. The atomic mass is 12. So the mass is the protons plus neutrons. So we could say that in an electrically neutral carbon atom, there are 6 protons and there are 12 minus 6 or 6 neutrons. Isotopes are atoms that have the same atomic number, but they have a different atomic mass. That's because they have a different number of neutrons. So for example, carbon-12 or 12C has 6 neutrons, whereas carbon-13 has 7 neutrons. There's 1 extra neutron there, so the atomic mass is a little bit bigger. In this case, it's 13 rather than 12. So the mass number minus the atomic number gives us the number of neutrons for the isotope. And the same case is true just looking at a normal neutral element that you would find in the periodic table. The mass number minus the atomic number gives us the number of neutrons. Keep that in mind. Radioisotopes are unstable forms of an element that break down over time. Radioisotopes decay and they release different types of energy, different rays and subatomic particles over time. Radioactive substances that are in the environment can harm cells, usually due to damage of the DNA, and that eventually leads to causing cancer. But radiation can be put to good use as well. We use radiation for a bunch of different things. For those of us that work in the lab, we can add radiation to a sample and we can use that to detect molecular changes. There are all sorts of different types of experiments that utilize radiation. We can use radiation to kill bacteria and viruses to sterilize things. And so radiation is frequently used to sterilize medical and dental products. It's used to sterilize food. We can use it for x-rays for diagnostic purposes, and we can use it for things like cancer therapy. So molecules, we said, are made of atoms that are bonded together. So a molecule can be made of the same atom, or it can be made of different atoms. And there are a couple of different types of bonds that we're going to look at that join atoms together. The first type of bond is the ionic bond. Atoms that are involved in an ionic bond either donate or they take on electrons from another atom. So the end result here is a stable outer shell. So we said the shell is a group of orbitals. So if it's the innermost shell, that stable number that we're looking to achieve here is 2. If it's any shell other than that innermost shell, the stable number we're looking for is 8. So we're only going to see 2 for 2 different elements, hydrogen and helium, the smallest 2 elements. All the other elements, their stable outer shell is going to look to have 8 electrons in it. So that's the goal of an ionic bond, to form a stable shell that has 8 electrons in it. Ionic bonds form between particles that are charged. Charged particles are called ions. And you'll see as we go through the course that the balance of various ions in our bodies is really important to our health. One example is sodium. We have to have the right amount of sodium in order for our bodies to function properly. If we have too much sodium, we end up with high blood pressure. What you see here is an example of an ionic bond between sodium atoms and chlorine atoms. So this sodium atom, if we take a look at its electron composition in its outer shell here has 1 electron in it. Well, 1 electron is not the same as 8 electrons. Remember, 8 electrons is the goal. So ideally, sodium would like to get rid of 1 of its electrons. Let's take a look at chlorine over here. Its outer shell has 1, 2, 3, 4, 5, 6, 7 electrons. Well, chlorine would really like to have 8 electrons. So if sodium and chlorine associate together, what you have is a donation of electrons here. Sodium is going to donate this electron here over to chlorine. And now sodium is going to have in its outer shell 1, 2, 3, 4, 5, 6, 7, 8 electrons. And chlorine is going to have in its outer shell 1, 2, 3, 4, 5, 6, 7, 8 electrons. So both of these atoms now have a stable outer shell. Sodium chloride is what you see over here on the left. It is table salt. The next type of bond that's going to be important for us is the covalent bond. Atoms in a covalent bond share electrons. So what happens is the electrons spend part of their time in the outer shell of each of the atoms that are involved in the bond. And so that results in a stable outer shell. Let's take a look. Here we have oxygen. We take a look at the electrons in its outer shell. 1, 2, 3, 4, 5, and 6. So it has 6. It would really like to have 8 electrons there. And if we take a look at hydrogen, here's its outer shell. Remember, hydrogen is one of the exceptions to the rule, so this shell can only hold 2 electrons. It has 1. So it would ideally like to have 1 more electron. Same thing for this hydrogen atom. So what happens if an oxygen atom and 2 of these hydrogen atoms get together and they each share an electron? So this hydrogen is going to share its 1 electron with oxygen. This hydrogen is going to share its 1 electron there with oxygen. And look what happens when we share. Here's hydrogen. It has 1, 2 electrons in its outer shell, so it's stable. This hydrogen has 1, 2 electrons in its outer shell. And take a look at oxygen. 1, 2, 3, 4, 5, 6, 7, 8 electrons in its outer shell. So oxygen is stable as well. So that's the end result of a covalent bond. We're getting that nice, stable outer shell of electrons. Similar thing here for 2 molecules of oxygen. Each has 6 outer electrons, 6 and 6, and when they share electrons, you can end up with, in this case, they share 2 pairs of electrons, or 4 electrons. So 1, 2, 3, 4 electrons, 5, 6, 7, 8 for this oxygen. 1, 2, 3, 4, 5, 6, 7, 8. So each atom of oxygen now has 8 electrons in its outer shell, and so each one is stable. So if we have a double bond, that's what you just saw. That means that atoms are sharing 2 pairs of electrons, like you just saw for 2 oxygen molecules. A triple bond occurs when atoms share 3 pairs of electrons. So we can represent these types of bonds in different ways, and there are 2 different types of molecular formulas or structural formulas that you can use to depict a molecule. A structural formula looks like what you see here. It uses straight lines in order to show covalent bonds between different atoms. So each line that you see in a structural formula here equals a pair of shared electrons. So here there are 1 pair of shared electrons. Here's a pair of shared electrons. Here there are 2 pairs of shared electrons, or those 4 electrons that we saw shared between the 2 oxygen atoms. The other type of formula is the molecular formula. The molecular formula only tells us what numbers are there of each type of atom in a molecule. So for example, H2O is a molecular formula. We know that there are 2 hydrogens there for every oxygen, but we don't necessarily know how those atoms are arranged. Next, I want to turn our attention to water. Water is the most abundant molecule in living organisms. It accounts for typically somewhere between 60 and 70% of an organism's body weight. Water is a polar molecule. What that means is that one end of the molecule has a negative charge and the other end of the molecule has a positive charge. And you can see that depicted in this little cartoon here. The oxygen part of water is slightly negatively charged, whereas the hydrogen parts of water are positively charged. Oxygen is the larger atom in water compared to hydrogens, so oxygen has a greater ability to attract electrons than the hydrogen atoms, which are a lot smaller. So the charged electrons stay a lot closer to the oxygen atom, so the oxygen becomes slightly negative at that end of the molecule, and the hydrogen becomes slightly positive at that end of the molecule. So you can kind of think of it like this little cartoon that you see here. Here's oxygen really big and strong. Here's hydrogen a lot weaker. And oxygen says, sure, we can share the electrons, but I'm bigger and stronger. Those electrons are going to be closer to me. And so here are the electrons. They're shared between the hydrogen and the oxygen, but they're a lot closer to the oxygen. Remember, electrons are negative, and so if the negative subatomic particles are closer to the oxygen, oxygen's going to have a negative charge, whereas the hydrogens are going to have a positive charge at that end of the molecule. Some other interesting things about water is that water is a liquid at room temperature. That doesn't really sound like a big deal, but most lower molecular weight compounds are gases at room temperature. Think about helium. Helium's a gas at room temperature. Another important property of water is that liquid water does not change temperature very quickly. Water has to absorb a lot of heat before it boils. It also holds its heat really well, so the temperature of water falls slowly. What that means for organisms is that organisms are protected from rapid temperature changes. It helps us to maintain our normal internal temperature. So water is a good temperature buffer. It prevents any drastic changes in temperature. Water also has a high heat of vaporization. That means that it takes a lot of heat in order to convert water into steam. And so that keeps the body from overheating. Another interesting thing about water is that frozen water is less dense than liquid water. Most substances contract as they solidify, but water does the opposite. Water expands as it becomes a solid. So in ice, water molecules form a well-organized lattice, like you see over here, and the hydrogen bonds in the lattice are farther apart than they were when we had liquid water. So this explains, because water expands as it's frozen, this explains why cans of soda burst in the freezer, why we have frost heaves on the roads once in a while, and why bodies of water freeze from the top down. Now that last point is really important if you're a fish. If you had bodies of water that froze not from the top down, you would have fish without any place to swim, right? So the tops of the lakes and ponds freeze and the water remains underneath so that the organisms that live there can still function. Additional properties of water are that molecules of water cling together, but they flow freely. So another way to put that is that liquids fill vessels. So that allows substances that are dissolved or suspended in water to be evenly distributed. That's going to become really important for something like blood. Blood is made up of 92% water, and then there are a bunch of different cells and proteins that are dissolved in that water. Water is also an excellent solvent for any molecules that are polar, and so it facilitates chemical reactions really well. So certain ions, remember those are charged molecules, they disperse really well in water because they have a charge and because water is polar. And so as these ions and molecules disperse in water, they move around the water, they collide with other molecules, and collisions causes chemical reactions to occur. So water is really, really good at allowing chemical reactions to happen. So what is the bond that holds water molecules together? It's not an ionic bond, it's not a covalent bond. The answer is the hydrogen bond. A hydrogen bond occurs between hydrogen that's involved in a covalent bond and another negatively charged atom that's in the vicinity. So what you see here are little molecules of water. So the red is the oxygen and the white are the hydrogen molecules. And so what you want to notice is that here's the positively charged hydrogen. It is going to associate with the negatively charged oxygen on another water molecule. And you have that happening for every possible interaction that you could have. This hydrogen over here associates with this negative oxygen, whereas this negative oxygen part of the water molecule here is associating with positive hydrogen here, positive hydrogen there. And so you have a really nice tight association of all of these different water molecules. Each hydrogen bond is a relatively weak bond, and so when you see them drawn, you typically see them represented by a dotted line like you see here. But overall, when you put together millions and millions of those weak little hydrogen bonds, you can have a pretty strong force. So here are just two different ways that we can look at water. So over on the left is the electron model. You've seen this one before. This tells you what's happening with the electrons. Remember, we are sharing electrons here. We have a covalent bond here between the oxygen and the hydrogen. So there's 2 electrons shared here. There's 2 electrons shared here between this hydrogen and the oxygen. And so each one has a stable outer shell. 8 for the oxygen and 2 for each of the hydrogen atoms. Here's another way you can view the same exact thing. This is the space filling model. So now you see your oxygen in red, your hydrogens in white, and you can see that it's written as a negative over at this oxygen end of the molecule and positive over where each of these hydrogens are. So the hydrogens are partially positive and the oxygen is partially negative. So that makes water polar. It has a positive and a negative end to it. So there are different ways that ions or molecules can react with water. Some of them are hydrophilic. That means water-loving. So these are ions and molecules that really like to interact with water. So think about food coloring. If you take a glass of water and you add a drop of food coloring is hydrophilic. You can give it a little shake, and that food coloring is going to disperse itself really nice and evenly throughout the entire glass. The other way that molecules or ions can behave is water-fearing. Those molecules are called hydrophobic, fearing, so they fear water. So these are molecules that are non-ionized, so they don't have a charge, or they're non-polar. so they don't have that charge differential across the molecule. And so they don't really like to interact with water. So a hydrophobic molecule you can think about as if you take a drop of oil and you put that in water. You could give it a good shake and you could kind of disperse the oil a little bit, but over time, those oil molecules are all going to find each other and group back together. They don't like to be in water. Another thing that we have to consider, this is going to be important when we look at the different systems of the human body, are acids and bases. When you take water molecules and you dissociate them or you break them apart, they release an equal number of hydrogen ions, represented by a little hydrogen here with a positive charge, and hydroxide ions, which is OH with a negative charge. So acids are substances that when they dissociate, they release lots of hydrogen atoms. Bases are the opposite. These are substances that take up hydrogen atoms or they release hydroxyl ions. So we can use what's called the pH scale. It indicates the relative acidity or basicity or alkalinity of a solution. So basically what the pH scale is a measure of the hydrogen ion concentration. The working scale for pH is between 0 and 14. 7 on the pH scale is considered to be neutral. If we have a pH below 7, that substance is acidic, whereas a pH above 7 is considered to be basic. So one thing you want to keep in mind is that the concentration of ions between each whole number on the pH scale is actually a factor of 10. It's not a doubling here, it's a tenfold change. So let's take a look at the pH scale here. So we'll start at a nice neutral pH of 7. So here's our concentration of hydrogen ions. That's just pH by definition. So a nice neutral pH, we say pure water. And let's go up on the acidic scale here. So let's go to a pH of 6. It would be something like urine. We got a little bit more acidic than that is black coffee. More acidic than that are tomatoes. Over at a pH of 3 are things like vinegar, cola, and beer. It's actually illegal if you work in a lab to take Coca-Cola and dump it down your sink because it's considered to be an acid and it's regulated waste. We get even more acidic than that is a pH of 2. Stomach acid and lemon juice would fall into that category. And then the pH of 0, the most acidic substance known is, of course, hydrochloric acid. So let's go back to our nice neutral pH of 7, pure water, and let's start to look at what's more basic than water. We have seawater, a little bit more basic than regular water. We have baking soda, more basic than that. The Great Salt Lake, start to increase our alkalinity even more. We have household ammonia, bleach is more basic than that, and finally sodium hydroxide, the ultra super basic substance that's known. So remember, this is a tenfold difference though. So between pure water and urine, there's 10 times more hydrogen ions here. So it's 10 times more acidic when we go from water to urine. So each of these is a tenfold change. Buffers are substances that tend to resist changes in pH so that the solution doesn't change in pH. It stabilizes the solution's relative acidity or basicity. So you're going to see when we go through the different body systems that the body has different buffers to prevent those changes in pH. And so buffers, what they basically do is they either take up extra hydrogen or extra hydroxyl ions that are in a solution so that they can keep the pH of a substance at a relatively neutral number. So there's a couple different kinds of chemical reactions that we're going to need to know. And here they are right here. So in order to make an organic molecule or to break down an organic molecule, we have to have a chemical reaction. So here are the two big ones. We have dehydration and we have hydrolysis. In a dehydration reaction, water is removed, and that removal of water allows us to link subunits together to form larger molecules. So this is the type of reaction we use to build bigger molecules. The reverse reaction is the hydrolysis reaction. We add water to something, and that breaks a larger molecule into smaller molecules. It's easy to remember this one. Hydrolysis, hydrolysis, water breaking apart. So add water, break apart. And if you can remember that one, then from there you can remember dehydration is the reverse. You would remove water, and that would link things together. Let's take a look at these reactions. So up at the top here, we have two different molecules, and we'd like to join them together. So there's a hydroxyl group on the end of this one and a hydrogen on the end of this one. So what we're going to do is remove the elements of water. So a hydrogen, and an oxygen gets removed. So water's removed. And we glue these two molecules together. That's our dehydration reaction. Then we have our other reaction, the hydrolysis reaction. So we have a nice big molecule. We'd like to break that apart into two different molecules. So we add the components of water to the reaction. And what happens? We put the OH on one molecule, the H on the other molecule, and now we have separated the molecule into two different molecules. So that's our hydrolysis reaction. So now that you know some basic chemistry, we're ready to start to think about what the different building blocks are that are coming together in order to form cells.